Last time we met, we ended on types of isomerism. So we talked about structural isomerism, and I explained where I mentioned that this is where the molecular formula of two compounds or two molecules are the same, but the structural formula or the way the atoms are arranged is different. So that's structural isomerism. Then we talked about now stereoisomerism. Now, stereoisomerism is interesting. So, before I can talk about that, so there you see the drawings that we have. Okay, let me do this so we can only have those drawings. So, you see glyceraldehyde, that's an aldose sugar. We explained what an aldose sugar is yesterday. Oh, sorry, the last time we met. And then the other one, that's acetone, isn't it? Dihydroxyacetone, which is a ketose sugar. So these ones have got the same molecular formula, which is which is C3H6O3. Okay, but when you look at how they are lined up, you see that they are, how the atoms are arranged, they are different, isn't it? So those are structural isomers. Now with stereoisomerism, this is interesting because this is how stereoisomerism looks. So I explained what things will qualify a molecule for stereoisomerism. So first things first, there has to be a chiral carbon. So another way to call, or rather to define a chiral carbon, this is a carbon atom that is attached to four different formula units. So you are looking at a carbon atom that is attached to four different groups of atoms, right? So if you've got a carbon atom that is attached to different things, different formula units, then that's a chiral carbon, or in other words you can call it an asymmetric carbon. So that's one of the those are some of the conditions that you need for you to have stereoisomers. So what we are having here is glyceraldehyde, and so you see that's glyceraldehyde, and when you look at that particular carbon in mention, you see that it's attached to four different groups of atoms, isn't it? You see there is the carbonyl group on top. Then we look at for the diagram on the left, you see that then there is the hydroxyl on the left, then the hydrogen on the down. Then you've got on the right, you've got CH2OH. Then on the right diagram, you've got again carbonyl group on top, CH2OH on the left, OH on the right, and then down hydrogen. So you see that those carbons, or that carbon is attached to what? To four different groups. Therefore, it's a what? It's an asymmetric carbon or a chiral carbon, meaning this particular compound, uh, so long as it's not symmetrical, so which means so long as you can't cut it in half and be able to see the different parts, or such that if it doesn't have a line of symmetry, don't worry, we'll discuss more of this in organic chemistry, but what this basically means is if you are looking at a compound, so let's just explain this. So if you are looking at a compound which you think has got a chiral center, right? Has got a chiral center or an asymmetric carbon, but you can actually have a line of symmetry. But you can have a line of symmetry in that particular compound, or in that particular molecule, then that cannot have a what? That cannot have a chiral, then that cannot exhibit stereoisomerism. So those are important things you want to know. So now you may be wondering, why is it that this one is levorotatory, this one is dextrorotatory, that's the L glyceraldehyde and D glyceraldehyde, and how do you assign these letters or these words to these two stereoisomers of glyceraldehyde? Don't worry, we'll discuss that in a short while. Now, it's very, very important to have an idea of number of isomers in any compound. And you may be wondering, why is this so much organic chemistry in biology? The reason in here is that, remember, in as much as you enter the medical field, you learn about pharmacology, right? Where uh, drugs are very sensitive. Drugs are very sensitive. So that's why you want to know if the particular drug compound that you are having, if it's going to have any stereoisomers, because like we will give examples of those a certain drug that used to be given to pregnant women so that they could reduce some of the symptoms of pregnancy. And what they realized is that it actually had the stereoisomer, which was actually exposing those children to harm. And up to now, those children are petitioning in courts so that they get compensation from those companies. So that just tells you just how important stereoisomerism is, and that's why it's in your medicinal biology. So anyway, let's get back to the basics. So those are number of isomers. So it's important to be able to figure out what are the number of isomers, because then you can test each compound that you have. You can be able to know what isomers, what isomers are you going to have in that particular compound, and then also you can be able to check them, are they harmful to people, and then that way your medications are going to be helpful. So now numbers of isomers in any compound is equal to 2 raised to power n minus 2, where n is the number of carbon atoms in the compound. So that applies to aldehyde compounds. So remember the aldehyde compounds, we're able to tell them to say this is where there is a hydrogen attached to a carbonyl group. In case you weren't there when we were discussing, you can watch the previous video. So that's basically about that. So using that formula, you can actually be able to figure out the number of isomers that you are going to have in a compound. So remember, the one which is 2 to power n minus 2, that's for aldehyde compounds. Then for the ketose compounds, is given by 2 to power n minus 3. So how they would ask questions in your test or exams, they will give you a structure. Okay, then they'll ask you to say how many isomers does this structure have. So what are you going to use? You just look at, first of all, look at the functional group. Is it an aldehyde or is it a ketone? Then from there, you then want to figure out, then what formula to use. Because for the ketone, it's 2 to power n minus 3, whereas for the aldehyde, it's 2 power n minus 2. So then using that information, then you can find your answer, where n, you know that it's just the number of carbon atoms. So you count the number of carbon atoms, then you've got your answer. So in case you're wondering how they can bring that question, that's how they can bring it. Okay, so we've already talked about the structural isomers, where they've got the same number and type of atoms, which is the same molecular formula, but different structural formula. And I explained to say, for instance, for those two molecules that we started with, okay, so these ones are glyceraldehyde and dihydroxyacetone. They have the same molecular formula, which is C3H6O3. So you remember, so you can see that on the dihydroxyacetone, the hydrogen on the top carbon should have, on the right should have an oxygen there. It was an error in the person writing the notes. Okay, so basically that's we've really explained this. So remember how to tell ketones apart is that the carbonyl group will be in the middle of the compound, whereas for the aldehydes it will always be at the end of the chain. As you can see here, it's on the end of the chain there on top for the glyceraldehyde, then for the dihydroxyacetone itself in the middle. Okay. Then, so we've done that. Then stereoisomers, I've already explained all these things that they're explaining. I've explained the asymmetric carbon atom and all that. How you can find the number of isomers for aldehydes, just a repetition, okay, which is 2 to power n minus 2 for aldehyde compounds. And I've already explained how you can figure out whether something is an aldehyde compound or it's a ketone. Okay, of course, n is the number of carbon atoms in the molecule. So let me just check to ensure that everyone is still in the meeting. Okay, so then that's sorry, wrong. Yeah, so then that's about that. Okay, now I mentioned that we should be able to also designate whether a particular sugar that you are looking at, it's D or it's L. So D, that's for dextrorotatory, and L is levorotatory. Now, stereoisomers, these are mirror images of one another, but you can't superimpose them. So the best example is look at your hand. If you put both palms of your hands up and you try to put the hands together, they can't superimpose on one another, isn't it? Okay, but they look similar. So they are mirror images of one another. You superimpose them with both palms up, they can't superimpose. And because of that, that's because they are mirror images of one another, and that's how stereoisomers are. So it's very, very important for us to designate whether this particular isomer is D, whether it's L. That's very, very important, because then it helps us, like I gave the other example earlier on, it can tell you to say, okay, it's the D isomer is the one that's important, right? Or for the medicine, because as you would see later on, most of the monosaccharides that we have as mammals are actually of the D isomer. And the enzymes that are responsible for their breaking down, for their metabolism, are also specific to the D isomer. So that's just what I explained a short while ago about why these things are important. Now let's talk about how you designate to say, okay, so this is D and this is L. So what we use is the orientation or the placement or the position of the OH group, which is the hydroxyl group. So to ensure that everyone follows, let's look at those two diagrams. Okay, we're talking about something else here. I think this should do it. So let's focus on these two diagrams there. So now, to determine which one is L and which one is D, you look at the position of the OH group. OH group, that's the hydroxyl group. Now, since we know that these particular compounds can have multiple hydroxyl groups, because we see that even in these compounds, there are two hydroxyl groups. So which one is going to count? So the one that counts is the OH group or the hydroxyl group around the carbon atom adjacent to the terminal alcohol group. Okay, so you are looking at something that's adjacent to the what? To the terminal, adjacent to the terminal alcohol group. So what's the adjacent? Okay, let's just take us further and then we'll see how this is explained here. Yeah. So you see this, right? So the terminal group that you are looking at here, that has got the hydroxyl. So the orientation of the OH group around the carbon atom adjacent to the terminal alcohol group or primary alcohol atom. So let me break this down. So what you are looking at is where is the hydrogen, sorry, where is the hydroxyl group? So hydroxyl group is the same as the OH, okay? Or that's the OH group. So you are saying on which side is the OH group? On the carbon atom that is next to the last hydroxyl group. Can I repeat that? That you are saying for you to know whether it is a D or L stereoisomer or isomer, you are going to look at the position of the hydroxyl group on the carbon atom that is next to the alcohol group that's towards the end. So as you can see in those diagrams, the terminal groups are those which are down there, and then you can see they are down there. Now, how do you know that these are the terminal groups? it's how you start counting these molecules, and that's something that we discussed the last time we met. We said that for the this, so we said that for the aldehyde, you always start from the carbonyl group. So meaning you start from one, two, three. You can see how they are numbered. Then for the ketones, we said since the carbonyl group is on the middle, so we endeavor to start from we just start on top basically just to count them. Okay, but when we talk about deeper organic chemistry, we usually want to uh, start from the side which is closest to the uh, to the carbonyl group. But in this case, since it's just three carbon atoms and both distances are the same, so we can start from either way. However, it will still give us the same case, isn't it? So we've understood how we are getting at the terminal and everything. Now, since our terminal, let's now come here. So since our terminal group, we've identified it. Now we are now checking for the atom that's for the carbon that's adjacent to the terminal group. So meaning the carbon that is next to the what? That's next to the terminal group. So you can see there on the left, that's that carbon there, the carbon number 2. Now, then we now go to the last part where we then ask ourselves to say, on which side is it? Is it on the left or the right of the carbon? So if it's on the right of that carbon, which is adjacent to the terminal group or the terminal alcohol group, then you see that actually, since it's on the right, since the hydroxyl group is on the right of that carbon, which is the second carbon in this case, then that's going to be the D isomer, dextrorotatory. That may be hard to remember, but when I explain the L, then you not have challenges and remembering the dextrorotatory. So then when you now go on the with the structure on the right, you then see that on the second carbon, the hydroxide is on the left. And so because it's on the left, so L, left starts with L. So this one is going to be levorotatory isomer or L isomer. So you see, to remember these things, just remember levorotatory left. The hydroxyl group is on the left of that carbon uh, which is adjacent to the terminal group. So left levorotatory L isomer, right? Then right dextrorotatory. Of course, if left is levorotatory, then of course it's direct that on the right it will just be dextrorotatory. So that's how you understand. So again, how do they bring these things on the exam? They'll just bring these particular structures. Let's say this one, and then ask you to name this. Just ask you to name it. Is it L or D? So you just look at that carbon 2. Is the hydroxy on the left? Yes, levorotatory. You see there it's on the right. The hydroxy group is on the right. It's D, dextrorotatory, glyceraldehyde. So that's how they bring these things on the exam. Has everyone understood that concept? Okay, so the presence of asymmetric carbon atoms also confers optical activity to the compound. So this is something that we'll discuss more in organic chemistry, but just to explain. So what happens is the fact that there is this stereoisomerism. When you uh, when you get these stereoisomers and then make a solution out of them, and then you pass a beam of polarized light. So polarized light is just a special kind of light that you use for this case. So when you put a beam of polarized light into that solution, if it's a dextrorotatory isomer, stereoisomer, then the beam of light will be rotated to the right. And if it's levorotatory, then the beam of polarized light to go to the left. So again here the concept is same. LL left levorotatory. So meaning the right just remains for dextrorotatory. So that's really about it. So now let's now talk about the hexos. So remember with what we said about the monosaccharides, how you name them, it comes from the name will give you the number, the idea, or it will give you the number of carbon atoms that are actually there. So if you hear trios, that means there are three carbon atoms. Here tetros, four, pentos, five, hexos, six. Okay, so hexos, these are just monosaccharides which have what? Six carbon atoms. So here is what we are having, and this can be represented in three ways. So what you see there, C6H12O6, that's the molecular formula. And you will realize that glucose, galactose, and fructose, they actually have the same molecular formula and yet have different structural formulas. So they are actually structural isomers. But let's just hold that thought there. We'll go into it later on. So here now we see glucose, right? So glucose can be represented in three ways. So there's the first one, which is the straight chain, just like a chain. Here it's the ring chain. Probably the ring chain is the most common that you'll be using. Then this one, it's an error. It's not supposed to be chain. It's supposed to be chair, because you see it looks like a chair, so it shouldn't be chain but chair, huh? Even the chair form. Now for this chair form, we usually make reference to it a lot. Uh, so when it comes to the concept of the chair form, we'll deal much more with it when we do organic chemistry in chemistry. So again, here these are examples of more straight chains. So you see that's fructose and that's galactose. So now again here, just by looking at these straight chains, you should be able to tell whether this is an outdose or a ketose. Because at this point, with what we've discussed, you should at least be able to identify that something is a ketose sugar or that something is an aldose sugar. You just have to be able to do that at this point. Makes sense, right? So can someone tell us what's on the left? Just don't the name, just whether it's an aldehyde or it's a ketone, whether it's an aldose or it's a ketose sugar. Anyone? Which one is the ketose? The one on the left? Okay. Then the one on the right? Okay. So just kindly explain to us why you think it's that, or how you came to that conclusion, just so that everyone can be able to benefit. So you can just tell us, oh, the carbon what, it's arranged like this. The carbon what is arranged like this. Okay. So that's a point, or those are points that on the second carbon, that's where the carbonyl group is. And then so that means that can't be an aldehyde, since for the aldehyde it always has to be on the uh, on the outermost part of the compound. It can either be up or down, but it will be on the outer. So that's true. So the one which is the ketose, that's the fructose. Then the one that's aldose, that's galactose. So by now I should be able to do that. So that's very encouraging. So yeah, so again here it's just basically just showing how the interactions occur for it to form the ring chain. But yeah, and these structures should actually be memorized, but I'll show you which structures are worth memorizing. But you need to know the structures of glucose. Then from the structure of glucose, you can pretty much derive the structure of galactose. But you need to know the structure of glucose. I remember we used to practice writing it. Okay, so now the ring form of glucose is called pyranose. So and then whereas so the key thing is that when you place these chains in water, so the chains of glucose, galactose, fructose, they'll form a ring. So now let's talk about, so we've already talked about the ring form of glucose, which is called pyranose. So one thing you realize about the ring form of glucose is that it's a hexagon. Okay, because why? It's got so you see all those parts where you're seeing 1 2 3 4 5, those are carbon atoms, right? So that's how you write things in organic chemistry. So where you're seeing those bends, corners, those are carbon atoms. So they have 6 carbon atoms. You can see that carbon atom is on top, but those forming the rings are 5 plus the oxygen. So it's a pyranose ring because it's a ring that's it's formed from it's got it looks like a hexagon. Let me put it that way. It's got 6 sides. It's got 6 sides. Then when you look at fructose in the straight chain, when you put it in water again, it will form the ring. However, even though the fructose can form the pyranose ring, like you can see there, but the pyranose ring of fructose is not stable. Okay, so you can see here that fructose that we had on top, it forms the pyranose ring. Remember, the pyranose ring is a 6-sided ring, isn't it? Or hexagon in this case, right? When you look at the structure, 6 sides. So you see that fructose has formed the pyranose ring, but the pyranose ring of fructose is not as stable as for glucose and galactose. That's why fructose usually will go to the more stable ring for it, which is the furanose ring. So the furanose ring, you see, that's the ring that's more stable, and that's the one that usually fructose is going to form. So when they ask which of the following ring is the one that fructose forms, you go for the furanose ring, because the way organic chemistry works is that things, molecules, compounds will usually exist most likely, or for the greater amount of time, they will exist in the form in which they are most stable. So fructose in its ring form makes a furanose ring because that's more stable. It can make a pyranose ring, it won't be very stable. So that's an important point to take note of. Then so a furanose ring is a pentagonal ring. So that's just basically saying it's got 5 sides. The ring has got 5 sides and is stable for ketosis, which makes sense because remember that fructose is a what? Is a ketose. And that's what I was saying. You need to be able to tell that this is a ketose, this is an aldose. Then a pyranose ring is a hexagonal ring, meaning it's got 6 sides and is stable for aldoses. And this makes sense because remember that uh, glucose, galactose, these are aldoses, and so that's why their most stable form or their stable form will be the hexagonal ring, which is the pyranose. So that's how they'll ask a question. Which of the following is most stable in the furanose ring? And then they'll put all those kinds of answers, but you know that the answer will be fructose. Okay, so hexose are monosaccharides with 6 carbon atoms, all have the simple formula C6H12O6. So they have the same molecular formula but different structural formula. So therefore these are structural isomers of one another. Okay, so these are structural isomers of what? Structural isomers of one another. Okay, great. So we've done that. Okay, so again, you can see hexoses such as, okay, so just to repeat something that we discussed sometime, each hexose has a backbone of 6 carbons in its chain, a carbonyl group, and at least 2 hydroxyl groups. At least 2 hydroxyl groups. Remember, those are things that we discussed last time. So some of the hexoses, such as galactose and glucose, have a carbonyl group at the end of the molecule. So they are what? Are therefore called aldoses. Okay? Are therefore called aldoses. And then with while other hexoses such as fructose have a carbonyl group on carbon 2, which is away from the end of the molecule and are therefore called ketoses. So pretty much what we discussed. So hexoses exist in 3 forms. Okay, let me just check if people are still on. Okay. So hexoses exist in 3 forms. So there's the straight chain, the ring form, and the chain form, but we've explained everything. So the carbons are still numbered as though they were in the straight chain. The carbonyl one is always drawn on the right hand side. I'm sure you have seen from those structures that we are looking at, right? You can see it always on the right hand side there. Okay, so glucose is there, galactose is there. Yes, yes. Okay, okay. So you're saying, is it possible for an element to have 2 terminal groups? Well, it just depends with what's happening on the ground. So what I mean by this is you can let me just check if it's still on. Okay, so it depends with what you have on the ground. For instance, if you had a compound such as this, and then you had, okay, so okay, so this is possible. So you start counting from 1, 2, 3, 4, and this will probably be something like butane 1,4 diano, since that's how these aldehydes end. So it's possible, but again, then that would no longer be a monosaccharide, because remember, but we'll discuss that more in organic chemistry. Because remember, we said what makes something to be a monosaccharide here. Each hexose has a backbone of 6 carbon atoms in its chain, a carbonyl group. So it just needs to have 1 carbonyl group and at least 2 hydroxyl groups. So if it has more than 1 carbonyl group, then we're talking about another compound or another group, because it won't have the characteristics of monosaccharides. It makes sense, right? Yeah. So generally, aldehydes, yes, they can exist. They can have 2 functional groups, both aldehydes. They can exist, but that will no longer be what? A monosaccharide. Because remember, these 3 things, these things, carbonyl group, at least 2 hydroxyl groups, they have to be, they have to be there for us to say this is a monosaccharide. The question be answered. Okay, so now we have okay, that's great. So now here we have these structures: glucose, galactose, and fructose. So like we said, galactose and glucose are aldoses. As you can see, the functional groups are on the terminals. whereas fructose, it's within the compound, so that's a ketose. So that's fructose there. Remember, for the number of isomers, what did we say we do? For the aldoses, we say 2 power n minus 2, isn't it? So you see there, that's why we are using those formulae for glucose and galactose, because they are both aldose sugars, whereas for fructose we are using 2 to power n minus 3 because it's a ketose sugar. Okay, so something that we had discussed earlier on. I just thought I should highlight that. And how to name these D and L, we've already discussed this. Okay, so we determined how to figure out the number of possible isomers. So this one that we are looking at is just number of isomers in general, right? In general, isomers in general. Then determination whether the hexose sugar is D or L. We remember we discussed that. Okay, then the important isomers found with glucose are D and L isomerism, pyranose and furanose ring structures. Okay, so let's go right into it. So you see what I was talking about. So that's the pyranose ring. So you see the pyranose ring is a what? Is a hexagon, whereas the furanose ring is a what? Is pentagon. And you realize that glucose and galactose, their stable form is in the pyranose form, whereas fructose, because it's a ketose, its stable form is what? Is in a furanose. So that's important to take note of. Okay, so a ring of 6 atoms is called a pyranose ring, whereas a ring of 5 atoms is called a furanose ring. Okay, so a pyranose ring is more stable. So it's the most stable ring formed for aldehydes, which is glucose and galactose. So that's basically mentioning what I had talked about. So you see glucopyranose. So glucose can try to can form pyranose and try to form the furanose, but it won't be stable. The furanose won't be stable for glucose, as you can see there, it's mentioned. Fructofuranose, you see, fructofuranose is the one that's going to be stable for the ketose, which is the fructose, but the pyranose is not going to be very stable for the fructose. Okay, so now here we can now talk about the alpha and the beta glucose. So now this is very, very important when the alpha and the beta, because this may interest you, but when we talk about the polysaccharides, the only thing that makes cellulose to be different from starch, it's because the starch has got alpha glucose, whereas cellulose has got beta glucose, and just because of that slight difference, we see the differences in cellulose. Starch can be digested, that's maize, yeah, those things, that's starch. But cellulose is those things we can't digest, which we call the dietary fiber. Okay, yeah. So now, what is an alpha glucose and what's a beta glucose? So the key thing here, you look at carbon 1. Now, where is carbon 1? Carbon 1 is the one that's going to be on the right hand. It's always on the right hand and it's above there or in the middle. So you can see there, right? The one there. So, and you have to know this. You just have to know this. You just have to know this. If the hydroxyl group or the hydroxide is below the ring, that's alpha. Okay, so you may be wondering, why are they saying below the ring? So you realize when we do organic chemistry that actually what we are looking at, okay, I just want to check that everyone is in. Okay, so when we do organic chemistry, you realize that these rings which are appearing to be in one plane, in the actual sense are not. There is actually those which are up. So there are actually those things which are up. Okay, so what am I doing? So realize that there's going to be those which are going to be up like that, and then there's going to be those other things which are going to be down. That's how these rings are. So there is always going to be these things which are going to be on top, and then there are also going to be other things which are going to be down. So that's what they mean when they say below the ring and when they say on top of the ring. So right, so if it's below the ring, the way it is here, it's alpha. If the OH, so if the OH is down, meaning that here on top we have hydrogen, then this will be alpha. Then if we have this hydroxide, then this hydroxide being on top, this is going to be beta or beta, okay, and the hydrogen is going to be down. So if it's beta, then yeah, oh, so if the hydroxide is above the ring, so that's what they mean above the ring, huh? So that's, yeah, so that's how you that's the context, I should say. Yeah, so that's what they mean, huh? So when they say hydroxide or hydroxyl group below the ring, so it's alpha glucose, huh? Then you see there above the ring, the OH is there, hydrogen is down, that's the beta glucose. And how do they bring this in the test? They'll just bring a glucose structure and ask you, what is this? So you should be able to know whether it's glucose, whether it's galactose. Yeah, so you first start looking at the carbon one is the hydroxide or hydroxyl group on top or down. Below the ring, alpha glucose. Above the ring, beta glucose. Okay. Please, is this clear? Is this clear? Then the other concept which is important is epimers. Now, the relationship between, okay, that's great. So the relationship between glucose and between glucose, mannose, and galactose, you know, it's epimerization. So what epimerization is basically is these are isomers which differ as a result of variations in configuration of the hydroxide and hydrogen on carbon atoms 2 and 4 of glucose. So if isomers are differing as a result of variations or as a result of differences in the arrangement of the hydroxyl group or the hydrogen atoms on carbon 2 and carbon 4 of glucose, these are known as epimers. Biologically, the most important epimers of glucose are mannose and galactose, formed at epimerization at carbon 2 and 4 respectively. So for you to understand epimerization, you need to understand the structure of glucose. So that's what I was saying, you just need to know the structure of glucose. Pretty much for the other structures. Yeah, so you see that structure of glucose, right? On the left, take a look at it. Look at carbon 2, look at carbon 4. So what they're just basically saying is the difference between, okay, the difference between, oh, I thought I didn't have a good diagram. Let me actually show the one that's here. Yeah, so okay, let's first start with mannose. So with mannose, the difference between, or how alpha glucose and alpha mannose, and why am I saying alpha? Because you see that hydroxide on carbon 1 is below the ring. Now you see this, you look at carbon 2, because carbon 2, that's where epimerization occurs for, to convert glucose into mannose. So look at carbon 2. In glucose, the hydroxide is where is below the ring, and the hydrogen is above the ring. Okay, I'm seeing them. Just check if people are there. Okay. So the so you see that on the second carbon, the hydroxide is below the ring in glucose, and the hydrogen atom is above the ring. Whereas epimerization, what happens is that there will be a change in configuration. When this change in configuration, when the hydroxide and the hydrogen atom on carbon 2, when they change their position, what was up goes down, what was down goes up. That epimerization at carbon 2. So you see there at carbon 2 there, the hydroxyl group moves up and the hydrogen goes down. And what you are now having there, it's as a result of the epimerization at carbon 2, you are now having mannose being formed. Makes sense, eh? Then when we now look at galactose, how galactose is formed, again these are alpha because remember on carbon 1, hydroxy is below the ring. So now when you look at galactose, galactose is an epimer of glucose, where at which point? At carbon 4. So look at glucose on the top left there. The hydroxyl what? Hydroxyl group is below the ring, whereas on the galactose it's above the ring. So you see that there is epimerization that has occurred at carbon 4. So they'll ask you, which of the following is formed as a result of epimerization at carbon 2 of glucose? Then they'll put answers mannose, maltose, just to confuse you, galactose. So you have to know at carbon 2 it's mannose, carbon 4 galactose. Okay, so to remember it in a funny way, just remember when you look at this, the word mannose, it's got how many letters? 7 letters, whereas galactose has got 9 letters. So look at carbon 2, 2 is smaller than 4. So carbon 2 goes with mannose, which has got fewer letters in its word, whereas carbon 4, which is the larger, between 2 and 4, so that's why it goes with galactose. Okay, I bet that helps. Okay, so that's really that. So now there's now the pentoses. Pentoses. Now these pentoses are very important because when we talk about DNA, we will always mention the pentoses because these are actually part of what makes our DNA. And so whenever we're talking about nucleic acids in the topics to come, we will revisit the pentoses. So pentoses, like the name entails, pent means 5. So these are monosaccharides, or you can say that, that contain what? That contain 5 carbon atoms. So pentoses are monosaccharides with 5 carbon atoms. They have the simple formula C5H10O5. Remember, we talked about the empirical formula for the for the monosaccharides, and I remember we mentioned something to say. Um, it's this, isn't it? Where N is the number of carbon atoms. So for the pentoses, carbon atoms are 5, so it's going to be C5H10O5, isn't it? So just a recap from what we discussed last time. But you can check the video for a full vision. So that's what we are having there. And again, a carbonyl group should be there. At least 2 hydroxyl groups should be there. So pentoses exist in both chain and ring form. So you see that here they've not mentioned of the chair form. Okay. So again, here you see that these are structural isomers of each other, ribose and deoxyribose. And so you see that the chains, um, even though these are actually aldoses, as you can see, their functional groups are towards the end, but the ring which they form, the ring which they are comfortable with is the furanose, and as you can see, it's actually a pentagon, because it's got 5 atoms, which are, or 5 sides, assume I want to put it. So what is the ring type that's formed by the pentoses? Both of them, ribose and deoxyribose, is what? Furanose. Now, where does the name come from why is it that one is called ribose and the other one is called deoxyribose? So what does it mean when we say oxygenated blood and deoxygenated blood? De- when we say oxygenated blood, meaning it's got oxygen, the blood has got oxygen, the red blood cells have got oxygen, right? But when we say deoxygenated blood, meaning it's lost oxygen. So when we say deoxyribose, as you will see, so you see the one there on top, that's the structure of ribose. Then when you look at the structure here, it's deoxyribose. So deoxy. So that means that it's an oxygen atom has been lost. So meaning that the difference between ribose and deoxyribose is the fact that in the deoxyribose, an oxygen atom has been lost. Makes sense, right? And where is this lost? It's lost at carbon 2. So look at the carbon 2 in the ribose, the one on top. You see on the carbon 2 there, below the ring, you've got hydroxy, whereas in the deoxyribose, you see that it's just hydrogen. So you see that a carbon atom has been lost. So this is very, very important, and it's got effects. Okay, so figure 1 shows the structural formula of two important pentals. Okay, we've talked about that. So those are being shown in both the straight and the ring form. Yeah, so deoxyribose and ribose are stable in the form of the furanose ring. I've already talked about that. So the main difference is just that deoxyribose has got one less oxygen on carbon 2. And ribose sugars form RNA, whereas deoxyribose sugars form DNA. RNA and DNA have very different functions in the cell. So you see that just that small difference, at carbon 2, it actually means that deoxyribose sugar is the one in DNA and ribose sugar is the one in RNA. So, are there any questions? Okay, uh, so disaccharides, that's what we'll be starting next time. I don't want to start it now and then end all the middle because we're just remaining with about less than 5 minutes. So even if we started and I discussed, it will be very hard to connect the next time we meet. So I feel it's best that we just reserve it here and then we can be able to start on a clean slate the next time we meet. Okay then.